Far beyond Neptune, beyond the blue geometry of the outer planets, beyond the familiar diagrams that make the solar system look orderly and complete, two machines are still moving through darkness. Voyager 1 and Voyager 2 are no longer visiting worlds. Their great planetary encounters are now part of history. Jupiter, with its storms and moons, Saturn with its rings, Uranus and Neptune revealed in brief electric glimpses. What remains is stranger. The Voyagers have become listeners. They travel through a region where sunlight has thinned into memory, where the sun is still present, yet no longer sovereign, and where the boundary of our home is written in invisible pressures rather than walls. The edge of the solar system is difficult to imagine because it is not a surface. There is no shining gate, no final orbit, no clean line where our system ends and the galaxy begins. The planets end long before the sun's influence fades. The Kuiper Belt dissolves into scattered bodies and frozen remnants. The Oort cloud, if we could see it, would surround the sun like a vast, ancient snowfall. Yet even these distant structures do not define the true frontier Voyager reached. The frontier is made of wind. It is made of particles released by the sun, of magnetic fields carried outward for billions of kilometers, of charged atoms pushed and slowed by the surrounding galaxy. What Voyager detected there was therefore more unsettling than a simple crossing. It found a boundary that breathes, compresses, trembles, and responds to storms born near the sun decades earlier. It found that the space around our star has a shape, a pressure, a skin. It found that interstellar space begins with a murmur rather than emptiness. And because those measurements came from instruments built in the 1970s, drifting farther from Earth than any human object ever sent, they carry a peculiar weight. They are messages from the edge of the sun's reach, recorded by aging machines that should have gone silent long ago. To understand what Voyager detected, we must begin close to the sun. The sun appears to us as a star of light, heat, and gravity. Yet it is also a continuous source of matter. Every second, it releases a stream of charged particles into space. This solar wind is thin by earthly standards, almost impossibly sparse, yet across astronomical distances it becomes a force of architecture. It flows outward past Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, and beyond, carrying with it fragments of the sun's magnetic field. The solar system is therefore not merely a collection of planets orbiting a star. It is enclosed in a vast moving atmosphere, a bubble inflated by the breath of the sun. Near Earth, the solar wind is already familiar through its effects. It shakes the magnetosphere, kindles auroras, disturbs satellites, and reminds modern civilization that space weather is not poetic invention. Farther away, the same wind continues its outward motion, though it weakens as distance spreads it thin. It is still fast, still charged, still magnetized. It carves a cavity in the surrounding interstellar medium, the diffuse gas and dust that fills the space between stars. This cavity is called the Heliosphere. It is one of the largest structures made by the sun, larger than all planetary orbits, larger than the diagram most people carry in their minds when they imagine the solar system. The heliosphere is often described as a protective bubble, and the phrase is useful, provided we remember that the bubble is dynamic, porous, and shaped by motion. The sun travels through the galaxy, and the heliosphere moves with it, pressing through interstellar material. Outside, the galaxy has its own magnetic fields, its own plasma, its own high-energy particles born from distant stellar deaths and violent cosmic events. Inside, the solar wind pushes outward. Between these two domains lies a region of negotiation. This is where Voyager became invaluable. No telescope could fully replace a machine passing through the boundary itself, tasting the particles and fields directly. Before Voyager reached that far country, scientists had models. They expected the solar wind to slow as it approached the surrounding interstellar medium. They expected a termination shock, where the wind falls below the speed at which pressure waves travel through it. They expected a heliosheath beyond that shock, turbulent and compressed. They expected a heliopause, the boundary where solar plasma gives way to interstellar plasma. Yet expectation in deep space is always provisional. Models are maps drawn before the traveler arrives. Voyager carried the traveler's instruments. The extraordinary fact is that both spacecraft, launched in 1977 for a grand tour of the giant planets, survived long enough to become probes of the heliosphere. Their original mission belonged to planetary science. Their second life belongs to cosmic geography. Decades after their cameras were shut down, after their images of moons and rings had entered textbooks, their particle detectors, magnetometers, and plasma wave instruments continued to speak. With reduced power, aging hardware, and instructions crossing billions of kilometers at the speed of light, the spacecraft slowly approached the place where the sun's wind loses its dominion. Voyager 1 encountered the Termination Shock in 2004. Voyager 2 crossed it in 2007. These were not visual events. No camera saw a surface rushing past. The evidence came through changes in particle speed, plasma behavior, magnetic fields, and energetic ions. The solar wind, which had raced outward for decades of travel time, began to slow dramatically. Its motion became disturbed. The spacecraft entered a region where the sun's outward pressure was being compressed by the material between stars. The first great threshold had been reached. The termination shock matters because it reveals that the heliosphere has weather. A shock in plasma is not a solid impact. It is a transition, a region where the properties of a flow change abruptly enough to leave a measurable signature. The solar wind arrives supersonic in a plasma sense, moving faster than disturbances can travel through it. At the termination shock, that flow is forced into a slower, hotter, more turbulent state. Energy once held in directed motion becomes disorder. The sun's wind begins to lose its clean outward character and enters the Heliosheath, the outer envelope of solar influence. Voyager 1 and Voyager 2 crossed the termination shock at different distances, a clue that the heliosphere is asymmetric and changing. The boundary is shaped by the solar cycle, by pressure from interstellar space, by the sun's motion through the galaxy, and by magnetic fields whose geometry is still debated. The edge of the solar system is therefore closer to a living ocean than a rigid sphere. It swells and contracts. It has regions of compression and relaxation. A solar storm launched during one phase of solar activity can take a long time to reach the outer heliosphere, carrying news of the inner system into the dark. Inside the Heliosheath, Voyager moved through a region no spacecraft had sampled before. The solar wind there had become slow and disturbed. Charged particles behaved in unexpected ways. Magnetic fields intensified. Energetic particles changed their distributions. The old image of the sun's influence thinning peacefully into space gave way to something more complex. A boundary filled with turbulence, pressure gradients, and a slow contest between the star and the galaxy. In this region, the sun was still present, though transformed. Its wind had become compressed, heated, folded, and slowed by the medium it had spent billions of kilometers holding back. For a viewer on Earth, the termination shock can be understood as the first warning that the solar system has an outer climate. Planets orbit within the inner weather of the sun, receiving light, radiation, and storms. Far beyond the planets, another climate begins, ruled by plasma and magnetism rather than seasons. Voyager did not simply leave a place. It entered a boundary system with its own structure. The great discovery was already taking shape. The solar system has an invisible frontier, and that frontier is physically active. The Heliosheath is the region where the solar wind grows old. It has traveled too far to maintain its original speed, yet it still carries the sun's identity. Its particles remain solar in origin, its magnetic field remains connected to the star, and its motion still belongs to the outward expansion that began near the corona. Yet the surrounding galaxy has begun to press back. The Heliosheath is therefore a place of exhaustion and compression where the sun's influence remains present through struggle rather than command. Voyager's passage through the Heliosheath revealed a region richer than early sketches suggested. The spacecraft measured variations in energetic particles, changes in magnetic field direction and strength, and signs of a plasma environment that could shift over time. At such distances, even small measurements carry enormous meaning. A particle count becomes evidence of cosmic shielding. A magnetic field reading becomes a clue to the shape of the heliosphere. A sudden drop in solar particles becomes a sign that the spacecraft has approached a new domain. The Heliosheath also revealed the presence of a magnetic barrier near the Heliopause, especially in Voyager 2's observations. As the spacecraft approached the boundary, the magnetic field intensified and cosmic ray behavior changed. The term barrier can sound too solid, yet it captures an essential truth. Magnetic fields in plasma can guide and restrict charged particles. They do not need stone or metal to form a boundary. In space, a field can become a wall for certain particles, a channel for others, and a record of pressures that no human eye could ever see. This was one of Voyager's most important lessons. At the solar system's edge, the geometry of invisibility becomes measurable. The spacecraft did not photograph the heliopause. It inferred it from physical changes. It found that the sun's protective envelope filters some of the high-energy particles arriving from the galaxy. Galactic cosmic rays, accelerated by distant violent events, strike the heliosphere from outside. Within the heliosphere, their intensity is moderated. Near and beyond the heliopause, Voyager measured their rise. The boundary of the sun is therefore also a boundary of exposure. For life on Earth, this has a quiet significance. The heliosphere is part of the chain of protections that make the inner solar system more stable than the galaxy beyond. Earth's atmosphere and magnetic field protect the surface locally. The heliosphere acts on a much larger scale, reducing the flow of certain galactic cosmic rays into the planetary region. Voyager did not discover a perfect shield. It discovered a vast, imperfect filter, an immense magnetic and plasma structure that participates in the habitability of our small world by shaping the radiation environment through which the planets move. The Heliopause is the boundary Voyager was destined to make famous. It is often called the place where the solar system ends, though that phrase requires care. Gravity reaches far beyond it. Comets in the distant Oort cloud may still belong to the sun across astonishing distances, yet the Heliopause marks the end of the solar wind's outward flow as a dominant plasma environment. On one side, particles originate primarily from the sun. On the other, the spacecraft enters the very local interstellar medium, the material between stars in the neighborhood of our system. Voyager 1 crossed the Heliopause on August 25, 2012. The announcement took time because the event had to be reconstructed through data. Voyager 1's plasma instrument was no longer functioning, so scientists relied on other signatures. A sharp drop in particles from the sun, a rise in galactic cosmic rays, and later plasma wave measurements that revealed the density of the surrounding medium. The crossing was historic because it marked the first time a human-made object entered interstellar space in the physical sense of leaving the heliosphere. It was also more subtle than the word crossing implies. The spacecraft did not pass through a visible membrane. It moved through a transition identified by instruments sensitive to the hidden grammar of plasma. Voyager 2 crossed the Heliopause on November 5, 2018, at a distance of about 119 astronomical units from the Sun. Its crossing was especially valuable because its plasma science experiment was still working at the time. That instrument could directly measure plasma properties, giving scientists a complementary view of the boundary. Voyager 2 confirmed that the transition from heliospheric plasma to interstellar plasma could be sharp, and it showed that the outer edge of the heliosphere was dynamic. The two spacecraft crossed in different directions and different solar conditions, producing a richer portrait than a single spacecraft could provide. The difference between Voyager 1 and Voyager 2 also revealed that the Heliopause is not a uniform shell. Voyager 1 experienced a more complex approach, including regions where solar particles diminished while magnetic field directions remained unexpectedly aligned. Voyager 2 found a thinner and in some ways cleaner boundary in the southern hemisphere, along with evidence of a magnetic barrier just inside the Heliopause. Together, the two spacecraft turned the boundary from an abstraction into a landscape of plasma physics. The edge of the solar system became a place with regional character. What does it mean for the sun's wind to end? It means that the outward stream of charged particles can no longer expand as the dominant flow. It is balanced and constrained by interstellar pressure. The sun continues to shine across that boundary, and its gravity continues farther, but its plasma kingdom has reached its outer limit. Voyager crossed into a medium no human craft had sampled directly before. The data showed that interstellar space near the sun is neither pure vacuum nor featureless darkness. It is tenuous, magnetized, structured, and responsive to disturbances traveling outward from our star. One of the clearest signs that Voyager had reached a new domain was the rise of galactic cosmic rays. These particles are atomic fragments moving at extraordinary speeds, often carrying energies far beyond those produced by ordinary solar activity. Many are thought to be accelerated by the shock waves of distant supernova explosions and other violent astrophysical processes. By the time they reach the solar system, they are no longer tied to their places of origin in any simple way. They arrive as messengers from the high-energy galaxy, stripped of context yet rich with physical history. Inside the heliosphere, galactic cosmic rays are partially moderated by solar magnetic fields and the outward solar wind. Their intensity near Earth changes with the solar cycle. During periods of strong solar activity, the sun's magnetic turbulence can reduce the number of galactic cosmic rays reaching the inner solar system. During quieter periods, more can enter. Voyager measured this modulation from the inside outward. As it approached the heliopause, the balance shifted. Particles associated with the sun decreased sharply, while galactic cosmic rays increased. The spacecraft was moving from the sun's filtered interior toward the rawer radiation environment outside. This rise did not simply confirm a boundary. It helped define the boundary physically. In ordinary human geography, a border may be a line on a map. In plasma space, a border is recognized through populations of particles. Solar particles and galactic particles behave differently. Their intensities change in opposite directions near the heliopause. Voyager watched one population fade and the other grow. That exchange is among the most elegant pieces of evidence for crossing into interstellar space. The phrase cosmic rays can sound abstract, yet the particles matter. They affect spacecraft electronics, contribute to radiation hazards for astronauts beyond Earth's protective magnetosphere, and participate in the chemistry and ionization of interstellar material. On cosmic timescales, they influence clouds where stars may eventually form. Voyager's measurements therefore connect the edge of our solar system to a larger galactic ecology. The boundary of the sun is not merely a local curiosity. It is the place where stellar weather meets the radiation history of the Milky Way. There is something almost literary in this exchange of particles. The sun sends its wind outward, filled with the memory of solar storms, magnetic cycles, and coronal eruptions. The galaxy sends cosmic rays inward, bearing the residue of distant catastrophes. The heliopause is where these two histories meet. Voyager detected the meeting through numbers, counts, energies, directions, variations across time. The poetry is ours, but the measurements are precise. Among the strangest things Voyager 1 detected beyond the heliopause was a faint plasma signal in interstellar space. The spacecraft's plasma wave system could not scoop up plasma as a functioning plasma instrument would have done. Instead, it listened to oscillations in the charged medium around it. When disturbances from the sun traveled outward and struck the interstellar plasma, they produced waves. Those waves allowed scientists to infer electron density, giving a measure of the material through which Voyager was moving. This was essential because interstellar space is sparse beyond ordinary intuition. A laboratory vacuum on Earth can be dense compared with the regions between stars. Yet sparse does not mean empty. Plasma can vibrate, electrons can oscillate collectively. A faint signal can reveal density across billions of kilometers. Voyager 1 detected plasma wave events after solar outbursts reached the interstellar medium, and later researchers identified a weaker, persistent plasma emission, sometimes described as a hum. This hum suggested that the very local interstellar medium has a continuous background signature, delicate but measurable. The discovery matters because it turned silence into data. Interstellar space had been imagined through telescopes, spectra, and theory, but Voyager gave humanity a direct local sampling. The spacecraft found that the density outside the heliopause is higher than the plasma density inside the outer heliosphere. This confirmed that Voyager had entered a different environment. It also showed that the boundary separates two plasma regimes with distinct properties. The sun's bubble is hot and thin in one way. The surrounding interstellar medium is tenuous in another, with its own density, magnetic field, and wave behavior. The phrase plasma hum should be treated carefully. Voyager did not record sound in the way a microphone records air pressure. Space lacks the dense atmosphere needed for ordinary sound waves. The hum is an electromagnetic measurement converted into a form that scientists can analyze and the public can sometimes hear as audio. Yet the metaphor remains powerful because it captures an unexpected truth. Beyond the sun's boundary, the galaxy is not mute. It has structure subtle enough to escape the eye and persistent enough to register on an instrument built before the personal computer age. In a script about Voyager, this is one of the most cinematic moments, though nothing visible occurs. A spacecraft passes beyond the sun's protective envelope and hears, in plasma, the faint signature of the interstellar medium. The drama lies in scale and patience. A machine built by humans, powered by decaying plutonium, receives vibrations from matter thinner than any earthly breath. From those vibrations, scientists infer the density of the space between stars. A frontier that once existed only in equations becomes a measured environment. Scientists expected the magnetic field outside the heliopause to change, and it did. Yet Voyager 1 produced a puzzle. When the spacecraft crossed into interstellar space, the intensity of galactic cosmic rays increased and solar particles dropped. But the direction of the magnetic field did not rotate as sharply as many had anticipated. The field remained more aligned with the heliospheric magnetic field than some models predicted. This raised questions about how the sun's magnetic field and the interstellar magnetic field interact near the boundary. The puzzle does not undermine the crossing. Other evidence strongly supported Voyager 1's entry into interstellar space. Instead, the magnetic field result enriched the problem. It suggested that magnetic fields near the heliopause may be draped, compressed, or arranged in ways that preserve directional similarities across the boundary. Plasma boundaries can be more subtle than simple diagrams. A field line can bend around a structure. A magnetic region can be shaped by flows and pressure. The heliopause may behave less like a wall and more like a layered magnetic interface. Voyager 2 added another crucial view. Its instruments showed a clearer transition in plasma properties and detected stronger interstellar magnetic fields beyond the heliopause. It also observed a magnetic barrier within the Heliosheath near the boundary, a region where magnetic field strength increased and affected particle transport. These findings helped explain how cosmic rays enter the heliosphere and why the boundary can differ depending on where and when it is crossed. A single edge became multiple phenomena: particle boundary, plasma boundary, magnetic transition, radiation filter. This magnetic complexity matters because magnetic fields are often the hidden skeleton of space. They guide charged particles, shape plasma flows, and influence how energy moves across immense distances. In the outer heliosphere, they help determine how the sun's bubble interacts with the galactic environment. Voyager measured these fields directly, giving scientists rare in situ evidence from a region otherwise unreachable. Every vector measurement, every fluctuation, every unexpected alignment became part of a larger attempt to understand the sun's place in the Milky Way. The result is a humbling correction to simple cosmic imagery. The edge of the solar system is not a clean celestial shoreline. It is a magnetic and plasma interface where the sun and galaxy interpenetrate through fields, waves, particles, and pressure. Voyager found a frontier governed by laws that operate beyond ordinary sight. The spacecraft's magnetometers became compasses in a sea without landmarks. Popular descriptions sometimes speak of a hot wall at the edge of the solar system, with temperatures reaching tens of thousands of degrees. The reality is more precise and more interesting. In plasma physics, temperature measures particle energy, not the sensation of heat an object would feel. A very sparse plasma can have a high temperature because its particles move rapidly, while containing so little matter that it would transfer little heat to a solid object. Voyager did encounter regions where plasma conditions implied high particle temperatures, yet this was not a blazing wall in any ordinary sense. This distinction is important for any serious telling of the Voyager story. Space can be intensely energetic while remaining almost empty. A spacecraft can pass through a plasma with a temperature of many thousands of degrees and avoid being burned because there are so few particles striking it. Temperature, density, and heat transfer must be considered together. The outer heliosphere is therefore a place where human intuition fails. Words borrowed from earthly experience can mislead unless they are handled with care. Voyager's data revealed that the Heliosheath and the region near the Heliopause contain complex plasma conditions. Particles can be heated at shocks and compressed boundaries. Energetic neutral atoms, charged particles, and magnetic fields all participate in the exchange of energy between the heliosphere and interstellar space. The boundary is physically active, yet it is not a furnace in the cinematic sense. Its drama belongs to measurement rather than spectacle. This subtlety actually deepens the wonder. A false image of a flaming wall is easy to imagine and easy to discard. The real boundary requires more attention. It is almost empty, yet structured. It is thin by human standards, yet powerful across astronomical scales. It can filter cosmic rays without being solid. It can be hot in particle energy and cold in felt experience. It can be crossed without visible sign, while the instruments register a profound change in cosmic environment. The edge of the solar system asks us to think like physicists rather than tourists. We must abandon the expectation that reality announces its thresholds visually. Voyager detected the frontier through the behavior of matter too thin to see, fields too vast to draw, and particles too small to imagine individually. The result is a boundary that becomes more impressive when stripped of exaggeration. Beyond the Heliopause lies the very local interstellar medium, often abbreviated as VLISM. This is the immediate galactic environment surrounding the heliosphere. It is part of the local interstellar cloud, a region of partially ionized gas through which the Sun is currently traveling. To speak of Voyager entering interstellar space is therefore to speak of direct contact with this local galactic material. The spacecraft did not leap into a generic cosmic void. It entered the specific neighborhood through which our star is moving. The VLISM is extraordinarily thin, yet its properties matter deeply. Its density, temperature, ionization, and magnetic field help shape the heliosphere. If the Sun passed through a denser cloud, the heliosphere could shrink. In a more rarefied region, it could expand. The radiation environment of the planets could shift across geological timescales. The solar system is not isolated from the galaxy. It travels through galactic weather, and the heliosphere is its moving envelope. Voyager's measurements of plasma density beyond the heliopause gave scientists a rare anchor point. Instead of inferring everything from astronomical observations, they could use data collected directly in the medium outside the Sun's bubble. Voyager 1's plasma wave detections indicated a denser environment than the plasma inside the heliosphere near the boundary. Voyager 2's functioning plasma instrument provided another set of measurements after its crossing. Together, the probes established that interstellar space near the Sun has measurable density variations and responds to solar-driven disturbances. The term local deserves emphasis. Voyager has entered interstellar space, yet it remains gravitationally close to the Sun on the scale of the Oort cloud. It will not approach another star for tens of thousands of years. Its interstellar journey is real in the heliophysical sense, but cosmic distance remains enormous. The nearest stars are still unimaginably far away. Voyager has crossed the Sun's plasma boundary, not the full gravitational estate of the solar system. This distinction enriches the story because it shows that a system can have multiple edges: planetary, magnetic, plasma, gravitational, and cultural. The VLISM is the first true galactic medium humanity has sampled in place. It is the material through which the heliosphere moves and against which the solar wind spends itself. Voyager's passage gives us a direct reference point for understanding how stars interact with their surroundings. Every star with a wind may carve a similar bubble. The Sun's edge becomes one example of a broader cosmic process. Stars making cavities in the galaxy, carrying their planets through interstellar matter like lamps moving through fog. For a long time, the heliosphere was often imagined as comet-like, with a rounded nose facing the Sun's direction of travel and a long tail streaming behind. Later observations from missions such as Ibex and Cassini complicated that picture, suggesting a more nuanced structure. Voyager added direct sampling from two paths through the boundary, while remote measurements of energetic neutral atoms gave broader views of the heliosphere's interaction with the galaxy. The shape of the solar bubble remains an active scientific question, and that uncertainty is part of the story. The heliosphere's shape depends on several forces. The solar wind pushes outward. The interstellar medium presses inward. The Sun moves through the galaxy. Magnetic fields drape around the heliosphere. Neutral atoms cross boundaries and exchange charge with ions, creating energetic neutral atoms that can travel long distances. Solar activity changes over an 11-year cycle in longer patterns. The result is a structure that may be asymmetric, variable, and far less simple than a smooth sphere or a long comet tail. Voyager's crossings demonstrated that the Heliopause distance can differ by direction and time. Voyager 1 crossed at roughly 121 astronomical units in the northern hemisphere. Voyager 2 crossed at about 119 astronomical units in the southern hemisphere. The closeness of these distances surprised some observers because the two spacecraft traveled in different directions and crossed years apart. Yet the details of their encounters differed, showing that similar distances can conceal different boundary conditions. The shape question matters because the heliosphere is our first line of contact with the interstellar environment. Its geometry influences how cosmic rays enter, how solar disturbances propagate outward, and how the Sun's presence is expressed beyond the planets. If we understand the heliosphere, we understand one example of how stars shelter their planetary systems. We also gain context for exoplanets orbiting other stars with different winds, magnetic fields, and galactic environments. Voyager did not solve the entire shape of the heliosphere. It gave us two narrow tracks through a vast boundary. That limitation is valuable to acknowledge. The spacecraft are like ships crossing 2 points of an enormous, invisible coastline. They tell us what the water and wind were like along their routes. They cannot map the whole ocean alone. Yet without them, the boundary would remain far more theoretical. Their measurements anchor every model to reality. One of the most remarkable aspects of Voyager's interstellar measurements is that the Sun still influences what happens beyond the heliopause. Solar eruptions can send pressure waves outward through the heliosphere. After long travel times, these disturbances can reach the boundary and continue into the interstellar medium, producing plasma oscillations detectable by Voyager 1. The spacecraft can therefore observe the after effects of solar activity even after crossing into interstellar space. This means the heliopause is not a clean divorce between star and galaxy. The Sun's storms can still leave fingerprints beyond its plasma boundary. A coronal mass ejection near the Sun may take months or years to propagate outward, depending on conditions, and its influence may eventually disturb plasma around Voyager. The data then reaches Earth many hours later as a faint radio transmission. A violent event near the sun becomes, after immense delay, a whisper in the instruments of a spacecraft beyond the solar system's protective bubble. The time scales are part of the grandeur. Light from the sun reaches Earth in about 8 minutes. Signals from Voyager take many hours to arrive. Solar disturbances traveling through plasma take far longer to reach the outer heliosphere. The system is therefore filled with delayed messages. The edge of the solar system receives news from the inner sun long after the original event has faded from human attention. Voyager records that delayed arrival and turns it into science. The boundary also remembers the solar cycle. The pressure of the solar wind changes as the sun moves through periods of greater and lesser activity. These variations propagate outward and reshape conditions in the Heliosheath. The Heliopause can move. Particle populations can change. Cosmic ray intensities can respond. The solar system's edge is therefore historical. Its present state contains the record of solar behavior from years earlier, stretched across distance and written in plasma. This is one reason Voyager remains scientifically precious, even with fewer working instruments. A distant spacecraft outside the Heliopause can monitor how the local interstellar medium responds to solar-driven disturbances. It can measure magnetic fields, plasma waves, and energetic particles in a region no other active probe has reached. Its aging electronics are now instruments of deep-time weather, listening for the sun's long echo in the medium between stars. The Voyager spacecraft were launched in 1977, built for a rare alignment of the outer planets that allowed a grand tour using gravity assists. Their cameras and instruments transformed human understanding of the giant planets. They revealed volcanic activity on Io, intricate rings around Saturn, the strange moon Titan, the icy drama of Uranus and Neptune, and the immense diversity of worlds beyond Mars. Yet the mission's most haunting chapter began after the images ended. As the spacecraft moved farther from the sun, power became precious. Their radioisotope thermoelectric generators slowly declined. Instruments were turned off one by one. Engineering teams learned to preserve warmth, power, pointing, and communication across distances that challenge ordinary language. Commands sent from Earth take many hours to reach the spacecraft. Replies take many hours to return. The machines operate with tiny margins, and each surviving instrument carries decades of institutional memory. The endurance of Voyager gives the boundary measurements emotional force. These readings were not the first act of a new spacecraft built for the Heliopause. They came from probes whose original mission had already become legendary. A device designed in the age of analog electronics and early digital control systems entered interstellar space in the 21st century. Its signals were faint, yet intelligible. Its discoveries were modern, even as its hardware belonged to another technological era. There is a temptation to speak of Voyager as lonely. The image is understandable, though loneliness belongs to human minds rather than machines. What is certain is that Voyager has become a measure of human reach. It has no engine capable of turning toward home, no camera returning new portraits, no destination that will greet it. It simply continues, carrying instruments, a golden record, and the consequences of a launch that occurred when the outer planets briefly offered a path. The edge of the solar system was detected by machines that were never guaranteed to last long enough to find it. That is part of the achievement. Science often advances through precision, planning, and design, but also through endurance. Voyager survived into a region where every measurement became unprecedented. Its aging became a scientific asset because time was the one requirement no later mission could easily replace. The Golden Record is often treated as the poetic heart of Voyager, a message to unknown recipients that may never exist. It carries sounds, images, greetings, music, and traces of Earth's life. Yet the scientific instruments tell another story of communication. They send no greeting to the stars. They speak back to Earth, reporting magnetic fields, plasma waves, and particles from beyond the sun's bubble. The two forms of message coexist. One addressed outward to possibility, the other addressed inward to knowledge. At the Heliopause, this contrast becomes powerful. Humanity imagined sending a symbolic self-portrait into deep space, and the same spacecraft returned an environmental portrait of our own boundary. The golden record says something about Earth. The instruments say something about the sun's place in the galaxy. One is cultural, fragile, and almost mythic. The other is numerical, compressed, and transmitted through the deep space network. Together, they make Voyager more than a machine of exploration. They make it a witness to both human imagination and physical reality. The measured frontier is perhaps more profound than the symbolic one because it changed our understanding of where we live. Before Voyager, the Heliopause was a theoretical boundary. After Voyager, it became a place with dates, distances, densities, particle populations, and magnetic puzzles. The solar system acquired an observed outer environment. The sun was no longer merely a star with planets. It became the maker of a vast bubble moving through galactic matter. This reframes Earth without diminishing it. Our planet is not only the third world from the sun, it is a world inside the heliosphere, inside a region shaped by solar wind and magnetic fields, temporarily sheltered from part of the galactic radiation environment. The sky above us is connected to a plasma boundary more than 100 times farther from the sun than Earth is. The safety and stability we associate with home extend through layers of protection, some local and atmospheric, others vast and heliophysical. Voyager's record may drift for billions of years, but its data has already arrived. That is the paradox of the mission. Its symbolic message is aimed at deep futurity. Its scientific message is urgent and present. The spacecraft will continue into darkness, but the boundary it detected has already entered human knowledge. The Heliopause is not fixed. It moves as the solar wind changes, as solar activity rises and falls, and as interstellar pressure varies along the sun's galactic path. The boundary Voyager crossed was the boundary at a particular time and location. It may have shifted since. It may shift again. This makes the edge of the solar system less like a coastline on a map, and more like the surface of a storm system seen from within. This movement complicates the meaning of crossing. Voyager 1 and Voyager 2 are moving outward, but the Heliopause can move as well. A spacecraft near the boundary might, under some circumstances, see conditions change as the boundary breathes around it. Voyager's data around the crossing periods showed that the transition can include variations, precursors, and layers. The edge is real, yet its reality is dynamic. The moving boundary also means the sun's relationship with the galaxy evolves. Over millions of years, the solar system passes through different interstellar environments. Denser clouds or different magnetic conditions could alter the heliosphere's size and shielding. These changes may influence cosmic ray fluxes reaching the inner solar system. The details remain complex, but the principle is clear. Our planetary system travels through a changing galaxy, and the heliosphere is the interface that responds. Voyager gives us only the current local chapter. It samples the very local interstellar medium of our era. Future probes, if they are ever launched with the specific goal of exploring the outer heliosphere, could map the boundary more deliberately, travel faster, and carry modern instruments. They could test whether the heliosphere has a long tail, a compact shape, or a structure still stranger than current models suggest. Voyager opened the door by accident of endurance. A future interstellar probe could walk through with intention. For now, the moving edge remains largely invisible except through measurements. We see it in cosmic ray counts, plasma densities, magnetic fields, and energetic neutral atom maps from distant missions. This invisibility should not make it feel less real. Much of modern astronomy concerns realities that cannot be seen directly. The Heliopause is one of them, a boundary detected through the behavior of the universe at its thinnest and largest scales. So, what did Voyager detect at the edge of our solar system? It detected the slowing of the solar wind at the Termination Shock. It detected the turbulent Heliosheath where solar plasma becomes compressed and disturbed. It detected the rise of galactic cosmic rays as the sun's shielding weakened. It detected the fall of particles born from the solar wind. It detected magnetic barriers, field intensification, and directional puzzles. It detected plasma waves in the interstellar medium, allowing scientists to infer density beyond the heliopause. It detected that the edge of our system is active, layered, and deeply physical. These detections form a single revelation. The solar system has an outer body. It is made of wind and magnetism, shaped by the sun's motion through the galaxy, and pressed by matter between stars. The planets occupy only the inner chamber of a much larger solar structure. Beyond Neptune lies a vast domain where the sun continues to work invisibly, sending particles outward until the galaxy finally slows them. Voyager mapped that transition through direct experience. The discoveries also corrected human instinct. We tend to define systems by what we can see: planets, moons, rings, asteroids, comets. Voyager showed that the invisible can be more defining than the visible. The sun's wind cannot be seen by ordinary eyes, yet it carves the heliosphere. Magnetic fields cannot be photographed directly, yet they shape particle motion. Plasma waves cannot be heard in air, yet they reveal density. Cosmic rays cannot be counted by vision, yet their rise marks a passage into another domain. At the edge, the solar system becomes a set of relationships rather than an object. The sun relates to the galaxy through pressure. The solar wind relates to interstellar plasma through shocks and boundaries. Cosmic rays relate to magnetic fields through modulation. A spacecraft relates to Earth through faint radio signals crossing billions of kilometers. The boundary is therefore not merely a place. It is an encounter between flows, fields, histories, and measurements. Voyager's greatest contribution may be this change of perspective. It taught us that home extends farther than the last planet and becomes stranger as it fades. It taught us that interstellar space begins gradually through particle populations and plasma densities. It taught us that the sun is surrounded by a shield that is alive with motion. And it taught us that even a machine moving through darkness can reveal the structure of the place from which it came. The edge of the solar system is difficult to love because it offers no image like Saturn's rings or Jupiter's storms. It asks us to care about a decrease in solar particles, an increase in cosmic rays, a plasma frequency, a magnetic field vector. Yet these measurements are among the most intimate portraits of our cosmic home. They show where the sun's breath ends. They show where the galaxy begins to press directly against the bubble that contains Earth. There is a quiet humility in the fact that our farthest explorers are small, old, and nearly blind. Voyager no longer sends photographs. Its great cameras have slept for decades. It cannot show us the frontier in color. It can only measure. In that limitation, the mission becomes more profound. The edge of the solar system is beyond ordinary beauty. It belongs to instruments, inference, patience, and trust in faint signals. The detections also place humanity within a larger physical continuum. We are not living under a sun isolated from the galaxy. We are inside a moving heliosphere, embedded in interstellar matter, exposed to particles from distant explosions, shielded in part by the same star that gives us light. Earth's environment extends upward into atmosphere, magnetosphere, solar wind, Heliosheath, Heliopause, and beyond into the local cloud. Home is layered. Voyager has simply traveled far enough to reveal layers we cannot feel from the ground. Perhaps this is why the mission still holds public imagination after so many decades. Voyager makes distance personal. It gives the abstract frontier a trajectory, a launch date, a speed, a radio signal, a human-made object moving farther away each second. The Heliopause could have remained a concept in plasma physics. Instead, it became a passage taken by two spacecraft with names, histories, and aging power supplies. Scientific abstraction became narrative without losing its rigor. What Voyager detected was the edge of influence. That phrase may be the closest human language can come. Influence fades before existence ends. The sun continues to exist beyond the heliopause as light and gravity, but its wind has yielded to another medium. The spacecraft crossed from one regime into another and reported the change. In doing so, it gave humanity its first direct knowledge of the threshold between a star's protected domain and the open galaxy. Voyager's future is quiet. Its power will continue to decline. Instruments will be shut down. One day, the spacecraft will stop transmitting, and the deep space network will hear no more from it. The machines will continue moving, but their scientific life will end. They will become silent artifacts on interstellar trajectories, carrying the golden record into a future too large for any practical expectation. Before that silence arrives, every remaining measurement matters. Magnetic field readings, plasma wave detections, and energetic particle data help scientists understand the local interstellar medium and the heliosphere's outer behavior. The data stream is sparse, but it is unique. No other operating spacecraft is so far away. No other mission has crossed the Heliopause and continued to report from beyond it. The Voyagers are old, yet their position makes them irreplaceable. There is a dignity in the mission's ending because it mirrors the boundary it studies. The spacecraft are fading gradually, instrument by instrument, watt by watt, as the sun itself becomes a small star behind them. Their signals arrive faint and delayed. Each transmission is a proof of survival across distance. Each packet of data carries information from a realm where the sun's wind has ended and the galaxy has begun to speak in plasma. The edge of the solar system will remain after Voyager falls silent. The solar wind will continue to flow. The heliopause will continue to move. Cosmic rays will continue to press inward from the galaxy. The very local interstellar medium will continue to receive disturbances from the sun. Future instruments may go farther, faster, and with greater precision. Yet the first crossing will always belong to Voyager. The first direct detection of that frontier will remain tied to these two machines, launched during a brief planetary alignment in 1977. Their legacy is therefore larger than distance. They taught us that the solar system has a boundary made of physics rather than appearance. They showed that interstellar space begins with measurable changes in plasma, particles, and fields. They transformed the edge of home from an idea into a place, and as they continue outward, they leave behind a final lesson. The universe does not need to be visible to be known. Sometimes the deepest frontier is detected as a faint variation in a signal, crossing the darkness from a machine almost beyond the reach of the sun.